You saw in part 1 of this series that the electron arrangement, which is known as electron configuration, partly decided by periods. I'll expand on this. Elements atoms are arranged in shells according to the period the element is in. Period 1 elements will have 1 electron shell, period 2 elements have 2 electron shells, and period 3 elements have 3 electron shells. The trend continues for all of the periods, right down to period 7. And the setup of the periodic table is so systematic and gives us so much information that you can actually switch off your brain after a while and simply look at the periodic table and you will instantly be able to give the electron configuration for the element that you've chosen. But before you can do this, a couple of rules you will either recall or you need to learn. Remember, we were just concentrating on the first 18 elements. It will be easier if I give you 3 rules to remember, but they're not in any way a chore. They're super simple to remember. And here's rule 1. I've already given you this. The period number gives the number of electron shells, and you can see here the number of shells is the same as the period number. Rule 2. Period 1 elements can have a maximum of 2 electrons, and then this electron shell is full. And just to make sure that you can follow this, here are those 2 elements from period 1, hydrogen and helium. Period 2 outer electron shell can have a maximum of 8 electrons this time and it's full, and the same goes for period 3 elements. And right at the end of each of these rows or periods, we have a noble gas. All the noble gases have the full outer shell of electrons, and this goes along with rule 2. Here's neon and argon, and notice I've written the number of protons and number of neutrons in numbers instead of colourful circles. It's far too time consuming and it's not necessary at this level because you know what's inside the nucleus are the number of protons and neutrons anyway. Rule 3 is the group number, so the group number is the same as the number of electrons on the outermost shell. Here are period 2 elements going from left to right, and you can see that the second number of the electron configuration corresponds with the group number they're in. And by now we should actually be moving on from drawing nice little circles inside the nuclei. Here's the first 18 elements, and let's try a problem looking at this shortened periodic table. Can you find the electron configuration of carbon, sulfur and aluminium using the 3 rules and the atomic number of each of these elements? We can do this together and fill in the table while looking at the periodic table. Carbon, period 2, then 2 electron shells. Carbon, group 4. Write 4 under group number. It has 4 outer electrons. Its electron arrangement is 2,4. I hope that makes sense. Aluminium is in period 3. Then it has 3 electron shells. Write 3 under period number. Aluminium is group 3, so write 3 under group number. Its electron configuration is 283. So let's think about this for a second. We can first add the number 2 because we know the element has 2 electrons in the first shell. We can write 3 but leave a blank. The 3 because the group number is 3, the blank we're not sure. But because it has 3 electron shells, that must mean the second electron shell is full. And from the rules already looked at, we know that that's 8 electrons. So its electron arrangement is 283. Just a little bit of arithmetic required there, that's all. So now, what about bonding? There are 4 types of chemical bonds that are taught at this level, and they are covalent, polar covalent, ionic and metallic. We will only cover ionic and covalent for now. The outer electrons are where the bonding happens. In fact, you can think of unpaired electrons acting like the glue that holds atoms together in bonding. So ionic bonding first. This type of bond takes place between metallic and non-metallic elements. Metallic elements are atoms like to lose an outer electron or electrons and become positively charged. If we use a common substance to explain this that you're familiar with, sodium chloride, it's an ionic substance, and we all know this as table salt. We use it every day to flavour our food. We can make sodium chloride in the lab as well, and you know that sodium chloride is a harmless and unreactive substance. It doesn't suddenly burst into flames or harm you in any way. It's a stable compound, and we can use this as one of our first principles of reactivity, in that when any atom reacts, it does so to become like a noble gas. And the thing we know about noble gases is that they all have complete or full outer electron shells. So here's sodium before it reacts. Its electron arrangement is 281. And here's chlorine before it reacts. Electron arrangement 287. And it's a non-metal. Sodium being a metal, it likes to give up its outer electron to make it like a noble gas. So it loses this outer electron here. And the chlorine atom likes to accept electrons again to make it like a noble gas. Here's some arithmetic. The sodium ion has 11 positive protons and 10 negative electrons. It becomes Na+. And the chloride ion has 17 positive protons and now 18 negative electrons. It becomes Cl negative. These two ions now have an electrostatic attraction between them. We have a positive sodium ion attracted to a negative chloride ion. The electrostatic attraction is an ionic bond and comes about because of the losing and gaining of electrons, so ionic bonding is due to a positive ion attracting a negative ion. I hope that makes sense. Covalent bonding is different, and that's because the atoms share a pair of unpaired electrons. The simplest example of this is the formation of a molecule of hydrogen. When these two hydrogen atoms come close to each other, the positive nuclei of both atoms strongly attract the other's electron. Again, it is because they need to be like a noble gas for stability. Because both of these atoms exert exactly the same force of attraction, neither can pull the other's electron away. The result is a perfectly shared pair of electrons between both hydrogen atoms. This is a covalent bond, and we call it a single covalent bond because it is a single pair of shared electrons. We can display a hydrogen molecule in these two ways. H2 is the formula for the hydrogen molecule. And just to add here, when you read about hydrogen in a chemistry textbook, it is referring to a molecule of hydrogen. Why? Because this is how hydrogen naturally exists, or exists in nature. The second way we can represent hydrogen with a line joining the two hydrogen symbols together. This line represents a single covalent bond, or a shared pair of electrons. Covalent bonding takes place between non-metal atoms. If you look at the way I have drawn these non-metal atoms, what you should see is electrons that are not in pairs. We call these unpaired electrons. The number of unpaired electrons a non-metal atom has is exactly the same as the number of covalent bonds it can form. I think that makes sense. Let's have a few examples. Here are two oxygen atoms, and here is an oxygen molecule. There are two pairs of unpaired electrons this time, here and here. We call this a double covalent bond, and we can also display it like this. And here's two nitrogen atoms. Notice it has one electron pair and three unpaired electrons. It can form three covalent bonds this time using the unpaired electrons. If a nitrogen atom finds itself next to another nitrogen atom, then both of them can share the unpaired electrons they have and form three covalent bonds like this. We call this a triple covalent bond and can display it like this. And this is its formula. Another common substance is ammonia, and ammonia consists of nitrogen and hydrogen bonded together covalently. So you can see some hydrogen atoms here and some nitrogen atoms here. Can you work out how they come together and form covalent bonds? Stop the video for a minute or two, while you think about it. Here's what happens. The nitrogen atoms have 3 unpaired electrons. The hydrogen atoms have only 1 unpaired electron each, meaning 3 hydrogen atoms can share their unpaired electron with 1 nitrogen atom. In all of these examples, if you rewind the video, notice that each atom is achieving the same electron configuration of a noble gas. In other words, it will have a full outer shell. Or its nearest noble gas, I should say, on the periodic table. Let's see what happens in the ammonia molecule if we cover up the hydrogen atoms, like this. The nitrogen then appears to have 8 outer electrons, just like neon. And then, if you cover up the nitrogen atom, each of the hydrogen atoms will appear to have the same electron configuration as helium. In the next video, I'll walk you through some examples of ionic and covalent molecules and the bonding, and a wee exercise. All for now.